Ever look at a string of letters and symbols in math or science? Like A equal E or maybe D VT, and just think, what is that even for?
Yeah.
What if those aren't just random clutter, but actually incredibly useful shortcuts?
Oh, they absolutely are.
Yeah.
Yeah. They can look a bit like, I don't know, complex code at first,
Right.
but fundamentally, they're just a really, really precise way, an efficient way to capture relationships between different things, different quantities.
Like a language.
Exactly. Think of it like a universal language for describing how stuff connects.
Okay, so for this deep dive, we're digging into a document that looks at exactly that.
Mm.
What mathematical formulas are.
Yep. How they're built, how you can kind of, change them around.
Manipulate them.
Yeah, manipulate them, and how they actually become practical tools.
So our mission together is to unpack this source material. We want to see how these formulas translate real-world connections into symbols.
And how, being able to work with them unlocks a deeper understanding why they're so much more than just like textbook exercises.
It's about getting comfortable with this language of relationships you mentioned.
Exactly.
Okay, so we'll start with a basic idea.
Yeah.
What is a formula? Then maybe look at how you'd write one from, say, a description.
Uh-huh. And then the really cool trick, rearranging them, changing the subject, they call it.
Right, to solve for different things. And then finally, how you actually use them, like plugging in numbers to get an answer.
Sounds like a plan. So, basics first.
Yep.
This source we're looking at, it defines a formula pretty simply. It's an equation, basically.
An equation.
Yeah, one that shows the relationship between two or more quantities, variables usually. The source actually calls it a translation from words to symbols.
Okay, translation. I like that. Let's make that concrete. Like the area of a rectangle. We all kind of know area A is length times breadth B.
Right.
So the formula ALB just writes that down symbolically.
Precisely. Or the distance example you gave, D equals VT. Distance equals velocity times time. It's just stating that relationship very clearly.
Simple ideas, but precise.
And it's not just for, shapes or physics. The document shows how you can take a description in words. Even something like 7 more than a certain number is 20.
Okay.
And translate that into symbols. X plus 7 equals 20.
Yeah.
You've captured the relationship. Or there's an example about ages.
Yeah.
After 7 years, the age of father will be 3 times the age of his son. You can turn that into an equation, like x plus 7 equals 3y plus 7, if x and your are their current ages.
Ah, so it forces you to be really clear about how things are connected.
Exactly. And that's where the power starts showing up.
Yeah.
Once you have that relationship down, like A equals LB, the next cool thing the source mentions is changing the subject.
The subject being the variable that's alone on one side, like the A and AL at B.
That's the one. And what's really neat is you use the same rules as solving any equation, keeping it balanced to rearrange the formula.
Okay, but why?
Well, because maybe you know the area and the length, but what you really need to figure out is the breadth.
Ah, okay. Got it.
So you take A equal LB, you do the same thing to both sides, divide by L, and boom, B equals AL. The relationship is the same, but you've reorganized it to find B easily.
So you're not just solving one problem, you're actually making a new tool from the old one. The source does this with perimeter of a rectangle, right? Yeah.
P
equals 2L plus 2B.
Uh-huh.
And if you wanted a formula to always find the breadth B, if you know PL, you just shuffle it around. Let's see. Subtract 2L, then divide by 2. You get B, P2L2.
Exactly right. You isolate the piece you need. It shows how flexible that captured relationship really is.
It's like one key opening different locks.
Good analogy.
Okay, and the final step is putting it to work, using numbers.
Yeah, substitution. Once you've got the formula set up for the variable you need, you just plug in the specific numbers you actually have.
Makes sense.
So the source gives an example, like C equals MXM if you're told X equals 5 and M equals 10.
You just swap them in?
Yep. C equals 10, 5, 10. Calculate it. C equals 50, 10, so C equals 40. Easy.
And the source mentions you could plug numbers in before rearranging sometimes.
Right, if you just need one specific answer. But changing the subject first gives you that general tool, ready for any set of numbers for the other variables. More powerful, usually.
Okay, let's do a quick recap then. We've seen formulas are these precise symbolic ways to capture relationships.
Between quantities.
We saw how you can translate descriptions into these formulas.
And then the power of rearranging them, changing the subject to solve for different bits of the relationship.
Right. And finally, substituting numbers to get actual concrete results.
And it's crucial to remember these skills aren't just for like math tests.
No.
Definitely not. They're fundamental tools for understanding things, analyzing, predicting outcomes. in tons of real-world situations.
Like what?
Oh, everything from, economic models, engineering
Yeah.
stuff, calculating medicine doses, even just working out your budget based on income and spending.
Okay, so back to that idea from the source. A formula, as a translation from words to symbols, it showed how things like distance, velocity, time, or even age differences, earnings, they can all be captured this way.
Yeah.
So if formulas are basically just structured ways of thinking about connections, maybe cause and effect, or how parts of a system relate, how many other complex things that you encounter every day could be, I don't know, simplified or understood better?
That's a great question.
If you could just capture the core relationship between their moving parts in some kind of formula. Something to think about.